Hey, isn't this a fancy venue? It's quite nice. I feel like I'm at some White House press dinner or something. Yeah, I'm Andrew Gerrand. I work on Go at Google in Sydney. And this talk is called Stupid Gopher Tricks. It's probably a bad title, but I sort of chose it and now I'm stuck with it. It's a talk about things that you might not know about Go, depending on how experienced you are with the language. And I hope that some of it you can find useful and actually add it to your sort of tool set of things you might want to do. But some of it is definitely things that you should never ever do, ever. And actually Rob wanted me to make sure I explicitly say that, and I'll point out where that's true. So I'm going to talk about the language, the libraries, and tools. I'll start with the language. So also this is very, very dense, code dense, so I hope that you've had coffee and that you can see the screens. So here's a type declaration. It's a struct type. And the part after type foo is a type literal. And we use type literals all the time. So there's also ints and slices and channels and so on. But it's the part after at the end of the type declaration. And I just wanted to draw that distinction because we commonly use type declarations in function signatures and variable declarations, and they're usually types like int. But it's also possible to use the type literal for structs in all of those contexts. So here I have a variable t that is a struct type, and these are usually called anonymous structs. So one common usage of anonymous structs is when you have like a one-off use for a struct, and I often use this when I'm populating a template with some data. So here we have a variable data that is a struct type, and this is the contents of the struct, and then I can pass it into my template execute function, and if I run it, I get the template. Oh, wait, what did that say? I forgot. It's also possible to use a map of string to empty interface to do this same thing. But unfortunately, in that case, you sacrifice performance. It has to actually allocate a map and populate it, which is a bit slower than populating a struct. And also, you lose the type safety of each of the values. So struct is far superior in this case. It's also nice to use anonymous structs when working with JSON objects. Often you want to encode or decode a JSON object, and you only need the struct representation of that object in one place. And particularly if you're like reading some big JSON blob and you only want to pull one field out of it, you might just want a single struct. So here's two instances, one of them encoding objects, where I have this struct type here in the marshal as the argument. And so it's a struct literal with some values. And so it encodes like that. And then on the flip side, I can declare a local variable data to decode into. And so I pass a pointer to that struct into unmarshal to get the same thing. And also, struct literals can be nested. So you can have an anonymous struct that has an anonymous struct as one of its fields. And so if you have some JSON data that has objects inside objects, you can achieve the same thing. And so we can see, it was pointed out in the review for these slides that George Costanza never actually was an architect, but he was the best architect one could aspire to be, I think. Go also lets you omit the type name when you have repeated literals like slices and maps. So in this case, I have this struct foo again, but where I have a slice of foo, I can actually list out each of the structs without putting foo here at the beginning, and that works. And when you combine this with anonymous structs, it actually makes it much easier. So if I have this slice s, which is a slice of this struct type, if I had to populate the type name every time, I'd have to do this big, ugly, anonymous struct in front of each. But fortunately, I can just omit that entirely. So T is definitely what you would do there. And that leads to much nicer instances of slices of anonymous structs. So if you have tests that have test cases, it's quite nice to declare them locally inside the test function instead of having to declare them outside with some, you wouldn't want to have like type index tests struct outside. You can just put it all in the one place. So here I have a slice of test cases, and I can iterate over them. If you want to go one step further, you can actually put that struct literal inside the range statement itself. So you don't even need the local variable. It's been pointed out to me that this is kind of harms readability a bit. You kind of, by the time you've started reading the middle of this struct literal, you've probably forgotten that you're actually in the middle of a for loop. So probably don't do that. And so embedded fields also fit into this picture. So if you have a field, for those of you who don't know, if you have a field in a struct that has no name, it's an embedded field. And embedded fields have the property that any of their methods and also any of their fields, if it's a struct that you've embedded, are now accessible as if they're part of the embedding struct, the outer struct. So here I have a type A, which has a single field S, a string, and it has a string method on it. And I embed that struct A in struct B. And then if I have an instance of B, I can assign to the B's field S, which is actually A's S. And if I call printline of B, it invokes the string method from A. And so that's a really convenient property, useful in many ways. But when you combine this with anonymous structs, you get an interesting kind of utility. So for instance, if you have global variables that need to be mutated and accessed from multiple Go routines simultaneously, one way of doing that safely is protecting it with a mutex. And a common way of doing that is you have your variable and then you have some mutex which has the same name, like with mu tacked on the end. And so whenever you want to access view count, you take the view count mutex and update the view count and release it. But if you embed that mutex in an anonymous struct, you get one single name in your global namespace, view count. And then it's clear from a documentation standpoint that the mutex protects those fields. And when you use it, you're only accessing this one name view count, which is a much cleaner little thing. We can also use structs, embedding in structs to implement interfaces in an ad hoc kind of way. So here's an example from the Camly Store project where there was a function signature which returned a read-seek closer, so the union of IO reader, IO seeker, and IO closer. But the programmer in this case actually only had a string, so they needed a string to implement read, seek, and close. And so it was Brad Fitzpatrick who wrote this. He created an anonymous struct with the embedded fields read, seeker, and closer. And then he used an IO section reader to wrap a string reader. So the string reader gives you a reader that yields the string. The section reader gives you a read seeker that reads the string. And then he composed that with an IO util nop closer, which is a standard library utility that gives you you give it a reader and it gives you a read closer that has a close method that does nothing. And so he's given it a nil reader so that he has a close method that does nothing, because closing a string doesn't do anything. And so this is particularly esoteric and strange, but I was told earlier today by someone that they could have actually used this somewhere. So I hope you can too. It's actually not that gross. And structs are not the only thing that we sort of can consider anonymous. Interfaces themselves can be anonymous as well. So, if you have an interface declaration type foo interface, the interface part is actually a type literal as well. And we see these all the time. We see the empty interface used pretty often, which is a type literal itself. But it doesn't need to be an empty interface. For instance, I can create this variable s that is an interface type which has a string method, and then assign something that implements stringer to it, and then invoke the string method on it. So this is a contrived example. But one way in which this is really useful is you can do an inline type assertion. So if you don't want to necessarily declare an interface for this one-shot type assertion, you can just do it inline like that. And this is something that I've seen pretty frequently. I've also seen people do this in type switches as well. So that's another cute little trick. So method values. Method values are what you get when you evaluate a method as an expression, and it gives you a function value that you can use, you can invoke and pass around like any other function value. And so if you take a type like bytes buffer and then evaluate a method on that type. So here I have a bytes buffer type name, and I take the write string method. It gives me a function value of this function signature. So I get write string is a function that takes a method that takes a string and returns an int and an arrow. But the method expression function has a bytes buffer as its first argument because that's the receiver for this method, right? So when it turns into a function as opposed to a method, I get the receiver as the first argument. And so it means if I want to call that function f that I've just created, I need to pass in a bytes.buffer as the first argument. And in this instance, I wrote buff write string because this is equivalent to just writing buff.write string and the string. And it's obviously not much cleaner, not much more useful. But if you evaluate a method on a value, so in this case I have a bytes buffer value, and I take the write string method as a function and store it in f. This time I get the same function signature but without the receiver as the first argument. So I just have a string. And that actually ends up being kind of clean. You could see it as a way of reducing the repetition of invoking that method, or passing it around, in fact, because this particular buffer receiver is now enclosed in that closure that you can pass around. And we'll see some examples of how that works. So if I run that, you get a little message. So one way in which this is practically useful is when using Sync.Once. So Sync.Once is a primitive that lets you perform a single task safely in a concurrent context. So if there are multiple Go routines that call the once values do method, giving it a function literal, only one of those Go routines will execute the function, and the rest will all block until that function has executed and then proceed. So it's great for doing like lazy initialization. If you have something that should only be initialized once, and it has to be initialized for every user of that thing, it's a great way to do it. So here's an example where I have a type called lazy primes, which inside it has a slice of prime numbers, but I don't actually want to compute the prime numbers and populate that slice until the first time somebody wants to use it. So there's this primes method that returns the slice of primes, and inside it calls the once values do method, passing in p.init as the do function, so as this function. And in this case, the method value p.init, it encloses this receiver into it, and so this init method is called on this particular instance of lazy primes, and you get to do the initialization. So that's one nice little clean example. And it's functionally equivalent to writing a function that calls p.init like that and placing that in the same place, if that makes sense. Another cute example is you can use method values to implement a bunch of HTTP handlers on the same type. So usually an HTTP handler method has to be called serve HTTP. But if you use each of these methods as a handler function as opposed to a handler implementation, you can, so here I have index, edit, and delete, 3 HTTP handlers on this server type. I can have a register method that takes the serve mux and registers index, edit, and delete, each as HTTP handler functions. And so in this case, the server is enclosed in each of these function values, and it's just like invoking the method. This is another example from the standard library internals. The exec package has a bunch of methods to set up standard input, standard output, and standard error on processes that are executed. And And the setup is different in each case, but the cleanup is the same for each of them. And so when the command is being set up for execution, we have this, this range loop over a slice of function values. And each of those function values is actually a method expression on the cummed type. So I'm doing this body for each of the standard in, standard out, and standard error methods. And so I call each of those methods, which are called setupfd, and then I do the cleanup for each in exactly the same way. And I can also then append each of those file descriptors to be cleaned up in the same way. So that's a real example. I want to talk about comparable types. So who here knows what the notion of comparability is in Go? All right, so good. Hopefully learning something. So the Go spec actually defines comparable as a concept. And basically any Go type that is comparable with equals or not equals is comparable. And the types that do satisfy this are booleans, ints, floats, complex numbers, strings, pointers, and interestingly, channels, structs, and interfaces are also comparable. And so here are some examples. If you have two integers, a and b, you can compare them. If you have two interface values whose underlying type is comparable, then you can compare those. So I'm assigning a and b to I and j, which are empty interface values. And when this comparison happens, it first compares the underlying type of the interface value, and then and if they correspond, then it compares the underlying concrete values. And also you can compare struct values. So in this case, I actually have a struct with an interface value inside it. And the interesting thing about comparable structs is that they're only comparable if each of their fields is also comparable. So that property sort of it's transitive. And so here's an example of a struct that is not comparable. So Q and R are both structs, but their only field is a slice, and slices are not comparable. And so we get a compile time error that the struct containing a string slice cannot be compared. So comparability manifests itself in a practical sense when we work with maps. Only comparable types can be used as map keys. And any comparable type can be used as a map key. So here's a common sort of thing you might see using ints as a map key. That works, obviously. A pointer type will also work as a map key. And also concrete struct types are usable as map keys. And also, you can also use a map of empty interface, which can take any comparable type as the key. And I just want to stress that you should never do this. If you ever see yourself doing map of empty interface to something, you're wrong. Just don't do it. There's no really good reason to do it. You sacrifice type safety. You open the door for things to explode at runtime. Don't do this. Good. Okay. But here's a real example of using a struct as a map key. So in the continuous build infrastructure for Go that builds Go on a variety of platforms like Linux and Darwin and so on, we have this notion of a builder rev. It's a struct with two fields, the builder, which might be like Linux AMD 64 or Darwin 386 or so on, and the revision, the Git revision that's being built. And we track those builds in various ways, and one of the ways we track them is in a map. So we have this like map called in-flight, and it's key. If we were doing this before Go 1, when we couldn't use structs as map keys, we would decompose that struct into a string form. And that works fine, but it means that every time we read or write from that map, starting with the builder rev, we need to allocate a new string. And it's allocating a string that is allocated already. It's in the map, and it's probably all over the code. And so in a high throughput environment, it's obviously a lot of pressure on the garbage collector that you don't need. But if we use a struct key, if we put the builder rev as the struct key, we can just use that builder-rev value itself as the key in the map. And so you avoid the allocation, and also the code is a lot cleaner to read. Interfaces as map keys are a little less often used, but here's a real example that I found on the internet, which is from Docker's code base. They have a package called Broadcast Writer that for every write, it implements writer, and then it lets you add writers to it so that when you write to the broadcast writer, it writes to all of the other writers. I'm not quite sure how they're using it, but it seems pretty interesting. But it has this map of write closes to empty struct. So they don't care about the value, they just want to track the write closes that they have. And when you add a writer, it adds it to the map, and when you do a write, it iterates over that map to do the writing. And if a write fails, it deletes that writer from the map. So that's a kind of cute little thing. And here's an example that's quite silly and very contrived, and you should never do anything like this ever. I have this type cons, which is like a Lisp cons cell. It has a value and then like a tail, car and catter, as they're called. And it implements string, which kind of it flattens it out. But I have this main function which has a map of cons to string, and I am constructing a cons cell and then iterating over a slice and then adding to that cons cell to create a series of nested struct values, which I then use as a map key and store a string, and then I'm printing the map key and the value, and so I get this string, and that was kind of what I was thinking while I was writing this example. But the interesting thing here is if I populate the catter field of my initial cons with something that's not comparable, like a slice of strings, and I run that, I actually get a runtime explosion. So I get a hash of an unhashable type slice of string. And so this is another reason why you shouldn't use interface values, and particularly empty interface values, as struct keys, because you open the door for runtime explosions like this, which are bad. All right, moving on to libraries. Who here has used the Sync atomic package? That's a little more than I expected, maybe a little more than is necessary. But who am I to judge, right? Earlier we saw the simple view counter where we were using a mutex to protect an int and incrementing that int while holding the mutex. Another way of doing that is with the atomic package, where you can atomically read and write and update values using your processor architecture's native primitives for doing these kinds of atomic operations. So if all you're doing is operating on a single word of memory, often the atomic package will yield a lot better performance. And in fact, a lot of the types in the sync package are constructed using these atomic primitives. And so you could use them in theory to construct your own concurrent primitives, but I think it's probably unlikely that you would want to do that. But so for a series of types, like int64, int32, and so on, there is a series of functions like add, compare and swap, load, store, and swap. And so in the case of the view count, I would have some global view count variable that is int64, and very important, I would document that this should be updated atomically. It would be nice if there was a tool to verify that. Maybe Francesca will talk about that later in the day, or maybe not. And then if you want to increment it, you can use add int64 and pass a pointer to that value. And so it will use the processor's atomic instructions to make that update and return the new count. There's also another tool in the atomic package called atomic.value, which lets you actually store any interface value and load and store that value in a concurrent, safe way. So, for instance, you could use this for sharing configuration. If you have some global configuration for your service, and you want each of those handlers to always see the latest version of that service, you would have a global config atomic value, and then you can store it using the config store method, passing in your new configuration. And then each Go routine that's running, so like at the top of each handler, if it's an HTTP server, for instance, you would call the load method. And load actually returns an empty interface value, so you have to convert that to, or assert that to its concrete type. And then you can read the configuration. If you try and store different types in the same value, it will cause a panic. And we'll see why right now. So when I first gave a version of this talk at the start of the week, someone asked, how does atomic.value work? And I was like, I don't actually know. And Brad said, read the source. And I read the source, and it was actually really interesting, so I thought I would show it here as well. Atomic.value itself is an interface value on the inside. So a single atomic.value has the same memory footprint as just any interface value, which is 2 words of memory. And the way that's represented by the runtime is actually 2 pointers. And this is a struct that's in the atomic package. It's not actually used by the runtime, but it's used by the atomic package as a representation for the same data structure in the runtime. So the data structure contains 2 fields, both of them pointer-sized. One of them represents the type of the interface value, so the underlying concrete type. And the other represents the data, and it's usually a pointer to the data of the interface value. And so for atomic.value to operate on an interface atomically, it actually uses atomic pointer operations to load and store each of these fields. But it has to do it in a sort of careful way. So if we look at the store method on value first, the first thing it does is check that you're not trying to store nil, because that's invalid. And then the next thing it does is it takes v, which is the value itself, and it takes x, which is the value that we're storing in the atomic value, and then it uses unsafe pointer to cast them into pointers of interface words. So instead of having an empty interface value, we now have a pointer to this struct, and we can modify these fields like any other struct, but we're actually operating on the internals of the interface value. And so once we have VP and XP, we want to store XP into VP. We need to spin. So most atomic operations will spin trying to do something until certain conditions are met. So we have a for loop that first loads the type field of our atomic value. And if the type is nil, it means that we haven't stored anything in that atomic value before. It's a new atomic value. And so the first thing we try and do is store a sentinel value. So we use compare and swap pointer to try and store an unsafe pointer of not uint pointer 0. So that not uint pointer 0 is uint pointer flipped with all bits to 1. So it's like max uint pointer, which is, on a 64-bit machine, it's whatever 2 to the 64 is. And so it's incredibly unlikely that a real type will ever have that value. I think it's pretty much impossible that you'll have that many types in a Go program. But if we're able to stick this sentinel value in the type field, then we can proceed and start storing the real value. That's what happens here. So if we stick the sentinel value in, we can then update the data field and then stick the real type in over the top. But if we fail to put the sentinel value in, it means that there is another concurrent store happening, and we need to loop back again and try again. So if we don't find that type is nil, which will happen if there's already a value in the atomic value, we instead need to check whether the type is the sentinel value, in which case there is another concurrent store happening, and we should try again. So we do a continue again. But if there's not the sentinel value, then there must be a real type value in there. And so we will check whether the type is the type we're about to store, and if it's not, we explode. So this is why you have to use a type of the same type whenever you store. And if it is of the same type, then we can go ahead and simply update the data field. So I hope that wasn't totally lost on you guys. But on the loading side, it's much simpler. When you're reading a value out, we do the same thing. We deconstruct the value into an interface word struct, and then we load the type. If the type is nil, or it's the sentinel value, then we're currently storing a value, and so we'll return nil. Otherwise, we can just load the data field and create a new interface word struct and stuff the type and data into that and then return it. All right. So with that said, usually you don't want or need any of this stuff in the atomic package. I know a bunch of you said that you'd used it. The chances are you might have been able to do it better without it. I suggest if you want to do anything, any concurrent synchronization, you should try channels or the sync package rather than the sync atomic package first. If you find those tools lacking, then you should start exploring the atomic package. But even if you are using the atomic package, don't try and write something like atomic.value, where you're reaching into the runtime. The representation of interfaces could change at any time. It's an implementation detail. So if you rely upon those things, you're just asking for trouble. Also, in showing that example, I didn't actually show the entirety of the implementation. While we were doing the spinning update, there were some calls to a function in the runtime itself, which would pin that particular Go routine to a particular processor, preventing it from being preempted by the scheduler, which is critical when you're doing these kinds of concurrent operations. You don't want another process to be scheduled in the middle of your concurrent update. And only packages in the standard library can actually hook into the runtime like that. So you can't write this code in the same safe way that you can here. But it's good to know how it works. Knowledge is really valuable. All right, so moving on to tools. I want to talk a little bit about testing, a couple of techniques that maybe you might not be familiar with. Sometimes when you're testing, you want to test the behavior of a process rather than just a function. Or maybe you have a function that affects the state of a process, and so it's not adequate to do that within the context of a regular test. So this function, crasher, it makes the process exit with a status of 1, prints a message first. Obviously, if we want to test that with the testing framework, it would just cause the test binary itself to exit, and we would never see any test results. And so one way to get around that is to have the test itself spawn the test binary itself as a subprocess. And so in test crasher here, if in this test function, we first see whether an environment variable, bcrasher, is set. If it is, we run the crasher function and return. So this is the pathway that will be followed if we're the subprocess. If we're not the subprocess, then we want to create the subprocess. So we use exec command to exec os.args of 0. So that's the test binary name itself. And then we pass the flag run test crasher so that we're going to execute only this particular test case. And then we add to the existing environment the bcrasher environment variable and execute it. And then to see whether the test was successful, we check the exit error and see whether it was a success or not. If it wasn't, then we will print out what the actual exit status was. So that's a very stripped down example, but subprocess tests can be useful in many ways. Analogous to subprocess tests, subprocess benchmarks. So Go has CPU, memory, and memory profilers. Who's used those before? Not enough, but enough. Some, okay. But the way those profilers work is they report information for an entire process. So if you have a benchmark that has 2 sides to it, so you want to test a server, you want to do a profiling on a server, you need some kind of client to access that server. And so you can use the same technique to spawn a subprocess that is a client hitting that server, and then you do the profiling only on the server part of that whole operation. So here's a real example from the HTTP package. where we spawn a child process to make requests to a server that's under test. And so we start off by turning allocation reporting on, and then we do the same thing as we did on the previous slide. We check an environment variable to see whether this process is the child process. And so if this environment variable is set, then we are. And in child process mode, we hit the provided URL n times, making HTTP requests, and there's some error handling and so on in there, which I've omitted. And then we exit, avoiding the rest of the benchmark function, which is the server side of the code. So it creates a HTTP test server that says hello world, and then it uses the exec package to execute the test binary itself, running the benchmark server, providing these environment variables. And so the end result is you can run go test running the benchmark with the CPU profile or mem profile flags and generate nice profiles that only include profiling data for the server side of this portion. If we had the client in the same process, we would have confusion over which parts of the profile reflected the client side and which parts reflected the server side. All right, and my final trick is GoList. Who here knows of GoList? Who here has used GoList? So GoList is a subcommand of the Go tool, and it prints package names for all the import paths that you supply. So if you say GoList bytes, it will just print bytes. If you say GoList with a wildcard, it will print all of the packages that match that wildcard. And there are some keywords like GoList std, which shows the standard library, or GoList all, which will show you all packages. And GoList has some interesting flags. It has a JSON flag, which will just dump out everything that the Go tool knows about that package. So there's tons of information in there. Useful things are the directory in which that package lives, documentation, what the build target is, whether the build is stale, so whether go install would actually update the build target or not, and also the files that comprise the package. So there's actually a struct in the documentation which specifies all of the fields available in that JSON blob. And so this is 1/3 of it. This is the next third, all the different kinds of source files that might make up a package. And also any CGO directives, dependency information, the package's direct imports, as well as all of its transitive imports. So that's imports and deps. It also includes error information. If there was an error in parsing the package will be listed as incomplete, and you can inspect what the error was in loading that package. And you can also see what the tests are and test dependencies and so on. And so with all of that information, you could dump it out with the JSON flag, but there's other ways of using that information. And one of them is with the -f flag, which specifies the formatted output of the GoList command. And the -f flag actually uses Go's text template package as its language. And the data that's supplied to that package is that package struct itself. So there's one template invocation for each line of output from GoList. So for instance, if I say GoList-f with just the doc field as my template for everything under the OAuth2 package, I get the first sentence of the documentation for each of those packages printed to standard output. Or I can use Go files as the template directive and see all of the Go files that comprise that package. And you'll see that the template package prints that slice with the little square brackets on either side. If I wanted to make that a bit cleaner, I could say GoList of join Go files by a space. So join is one of the available template functions documented in the template package, and then I can see those file names without the brackets. And then once you introduce template logic, you can start testing for conditions, and you can start filtering on the packages that are output. And so if I wanted to find the standard library packages that don't have documentation strings, I could have a template directive that is, if not doc, print the import path. And so for the standard library, that just shows 2 internal packages. Even though they're internal, they should probably have docs. But it's probably worth running something similar over your own code base and see where your documentation is lacking. It's also possible to find packages that depend on a given package. So in this template directive, I'm iterating over the dependencies, and if a particular dependency equals the OAuth2 package, then I'll print the import path. And so this shows me all of the, and I'm doing that for all packages in my workspace. So I can see all of the packages that I have that depend on OAuth2. And so I can see that some of the continuous build infrastructure uses the OAuth2 package. And that's really useful if I'm making some updates to OAuth2 and I want to see what packages might be affected by that. It's also nice to be able to list which packages are broken in some way. So if I pass the -e flag, GoList will not print errors to standard output and continue working even if it encounters errors. So that's critical for this example. And my template function is, with error, just print the error string. And so for each package that has some error state, I can see what the error condition is. And among other things in my workspace, I found that I had an old version of OAuth2 under the old import path that the Go tool doesn't like, because there's an import comment that says it should be called golang.org/x/OAuth2. And so that's another one that you might want to run over your own code. But once you introduce shell scripting into GoList, things start getting even more interesting. GoList's output by default lists import paths. And GoList's command line takes import paths. So you can very easily use the output of GoList as the input to another GoList command. So for instance, if I wanted to run all the packages, all the tests for the packages under my working directory, I would say go test /.. But if I want to run all the tests of my packages but not my vendored packages, I can say go list of those packages and then do an inverse grep for /vendor and then use that as the arguments to go test. Or if I wanted to just test the dependencies of a specific package to make sure that everything, if I'm encountering some weird bug and I want to make sure that all my dependencies are all okay, I can say go test of a go list of all the dependencies for this given package. If I wanted to do the same thing, but I don't want to waste my time running standard library tests because I'm running the stable version of Go and I trust that the tests pass, I can do the same thing. I go list the dependencies for OAuth2, but this time I do another go list to filter that dependency list, where I'm saying if this package is not in the Go root, print the import path. So it will only give me import paths that are outside the Go root. And then I pass all of those into Go test. But I got to go a step further, of course. If you wanted to print the line counts for a given package or a set of given packages, you could do this. You have a bash for loop, which iterates over each package in the OAuth2 repository in the variable package. And then for each of those, I do a go list with a format of each Go file in that package, and I add the package directory to the front of that Go file. So this command will give me all of the absolute paths of all of the Go files in that package. I pass those into word count -l, and then I use tail to trim off the very last line, which will be the total, or a single file if it's just a single file in the package, and then use trusty awk to print only the count and the package name. And then finally, once that's done, I can sort them all numerically and see that the Google package in the OAuth2 repository is the largest one, shortly followed by OAuth2. Something like this I might consider actually adding as a shell alias because it seems like it might be useful. And so for my final trick, I thought I'd do something funny, which is writing a single command line that generates an SVG of the dependency graph for a particular package. So this uses GraphViz. GraphViz has a very simple declarative language for specifying graph information, and then it turns it into pretty things like this. And so if I, in this instance, I'm doing a go list of, I'm doing a go list to get the dependencies of the time package and supplying the time package itself as the arguments to another go list that iterates over each of the imports of each of the packages to output a set of lines that say this package imports this other package. And actually, if I want to show what that looks like, I can run that on another command line. Yay, OS 10 updates. If I run that, you'll see that's the output, and that's the input that I would pass into the dot command. And so, I hope you can see that the Go list is actually a really powerful tool, and maybe it's something that you might want to start using. So there's much, much more. I have more sort of crazy ideas, and there are more interesting corners of Go's libraries and tools and even the language itself. And so I challenge you to do something similar. Maybe you can find even more interesting and strange things to do with Go. So the interesting thing is about all of this is all of these features are all documented. So it's not like there's sort of some corner hidden away. If you actually read the docs from beginning to end, you would find a lot more of these kind of things. So I encourage you to do that and have fun. Thanks. I'm also happy to take any questions with the microphone coming around.
Hi, Andrew. So on the broadcast writer slide,
yes.
If you could show it up again. I wanted to amplify one of the caveats you made about using a map keyed by empty interface. That example actually shows a map keyed by a non-empty interface. I think it was a writer.
This one?
Yeah, a write closer. So there's a problem here, which is that it's accepting write closers from outside the package. Let's see if the laser's not working. There it is. Okay, so it's accepting writers from clients, and then it's putting them in the map. And there's a consequence of that is that if a writer is not comparable, it's going to panic at runtime. And yeah, that's nowhere documented, and generally people don't document that kind of thing. So it's just another reason why you shouldn't put interfaces as map keys.
Yeah. Did everyone catch that? Because if this writer that the user is providing that I have no control over, if its concrete type is, say, a slice or a function, then this will explode at runtime. And I don't recall anything in the documentation of this broadcast writer package that said that. The other caveat that I would say about this particular implementation, and sorry to any Docker folks who might be here or watching, is iterating over the writers in a non-deterministic order also seems kind of surprising. I would expect all the subsequent writes to happen in the same order as the writers were added.
Do you know why slices are not comparable?
Yeah, so slices are not comparable because there's no obviously correct way to compare them. So there are different options. Slices themselves are a form of pointer. They point to a backing array. And so you could compare the slice header. So you could say, if this slice points to the same region of memory and it has the same length and capacity, then it's equal. That's one way of doing it. But that's not actually a particularly useful way of doing it, because often when we want to compare slices, we actually want to compare their contents. And so I think that would lead to surprising behavior where you would have two slices that point to different arrays that have the same values, but the slices are not equal. And so that's confusing. Another approach would be to compare the underlying arrays, and so actually iterate over the values pointed to by the slices, and then check whether they are equal as well. One reason that's not desirable is it's slow, and it can be unexpectedly so. And also, I might be wrong, but I think we don't have any other such similar comparisons that have this kind of unbounded complexity, right? It's sort of, the time it takes to do that comparison is linear to the size of the underlying arrays. Sorry? Oh yeah. Wait, it's cyclic? Oh yeah, if you have a slice that points to itself, what does that mean? And what if you have a slice of slices? Or what if you have a slice of structs with slice fields? You know, it kind of becomes really confusing. So just like we don't follow pointers when we do pointer comparisons, we just compare the pointer values themselves. We can't really follow slice values in the same way. And that was a deliberate, we definitely talked about doing that. And there are arguments for actually doing it, but in the end we erred on the side of predictability and simplicity.
What about letting the programmer define the comparable on its own struct? Like at the moment there is no support for that, but has been any discussion?
Yeah, so the question was, why not let the programmer define equality, basically, or another proposal has been allow the programmer to implement like some hashable method so that you could put arbitrary types into a hash map. The latter is kind of not that necessary anymore since we have struct keys in maps. The former, making arbitrary types comparable, it would be somewhat unprecedented in the language. So once you sort of head down that road, you start talking about making arbitrary types rangeable. You know, like you could have your own collection types that work with the range keyword. And it's definitely something that's been discussed, both during the language's original design period and also subsequently at length. But the general feeling is that it sort of steps up a level of complexity and magicness that isn't there right now. Like I know that if I'm comparing two values in Go, I know what that means at a programmatic level. I know that it's not invoking some arbitrary piece of code that's doing the equality comparison. And I think there's a really nice readability benefit to being able to look at a piece of code and see I can look at this expression and I know that it's basically just a comparison in assembly, and that's what's happening. I don't have to follow a potential equals method somewhere. And so keeping that level of magic out of the language was a deliberate design decision, generally through experience working with large code bases where such abstractions can lead to confusion. Any other questions? Nope. All right, thanks very much.